Hey there, this is Andrew, and today we're going to go over the N25 marks paper 3. Question 1 is on curve sketching. Even though this question is taken from STEP, it is not too challenging as you have access to your GDC. And that's also why I have Desmos to the left. So in part A, you're asked to differentiate G. Let's do it step by step very carefully. The derivative of ln of u is 1 over u times du. The derivative of its second term can be found using the product rule. Simplifying the first term, simplifying the second term. Now we want to put it all over the same denominator. To do this, we must multiply the first term by 1 plus x. The second term is negative x squared minus 2cx plus minus c. And that will give you the printed answer. Part A2, show that the function has positive gradient for all positive x when c is greater or equal to a half. So if c is greater or equal to a half, g prime of x becomes is greater or equal to x plus 1 by 2 divided by this guy. If x is positive, this means that x plus 1 has a positive, x plus a half is also positive. The numerator is positive, the denominator is also positive. Therefore, g prime of x is positive. Similarly, in part 3, find the values of x for which the function has negative gradient. G prime of x is less than or equal to 0 if and only if this guy is true. The denominator is strictly positive. We have demonstrated this earlier. Therefore, for this to be true, this has to be true. We also know that x is positive. Therefore, let's isolate x. So we know that x is for c between 0 and negative a half. This means that 2c minus 1 is less than 0. This means that x has to be greater than negative c divided by 2c minus 1. because you're dividing both sides of an inequality by a negative value. Moving on to part B. Now you're asked to sketch the graph for positive values of x, the graph of g when c is 3/4 and when c is 1/4. So this is where Desmos is going to come in very handy. So for c equals to 3/2, if c is equal to 3/4, we are only interested in the part where x is positive. The graph should look like the right branch of this curve. It will take the x-axis as the horizontal asymptote. If c is 1/4, based on the result that we have obtained earlier, we should expect a negative gradient for some values of x. So let's test our hypothesis. We can see that it has a local maximum when x is equal to 0.5. And it has a root at around 0.25. Before it takes the x-axis as the horizontal asymptote. Easy peasy. Part C. In this part, you're asked to consider ln of f to show various results. So, ln of f is equal to x plus c times ln of 1 plus 1 by over x. Let's take the derivative of this. The derivative of the right-hand side can be found using the product rule. So let's simplify this just a little bit more. If you pay attention, this is the curve that we were given in part A. This is also why we were doing a lot of calculations and a lot of proofs up here. So, C1. Show that f is decreasing when c is greater or equal to a half. Sure. So if c is greater or equal to a half, this means what? This means that g of x has positive gradient for Ox. So g of x is greater than 0 for all positive x. Furthermore, we know that 1 plus 1 over x to the x plus c also has to be positive for all positive x. You can either plug it into your CDC if you're not entirely sure, but you can see it is strictly positive. Therefore, f of x, g of x is also positive. Wait, it has positive gradient for. Oh, sorry. Okay. C1. We want to show that f is a decreasing function when c is greater or equal to a half. What happens when c is greater or equal to a half? We get a curve that is similar to this guy. And as we can see, the graph of y equal to g of x is strictly negative. This is basically graph B1. Furthermore, looking at the function we have here, we can say that f of x is strictly positive on this interval. You may want to include a sketch of the function if you want to convince the examiner. And therefore, f prime of x is less than 0, and therefore f is decreasing. C2. Show that f has a turning point when c is between 0 and 1 by 2. If c is between 0 and 1 by 2, we can see that the graph of y equals to g of x. We can see that the graph of y equals to g of x has a root. Has one root. We also know that f of x, let's say, let's put 1 by 4. F of x is also strictly positive. That means that there is a value of x where f prime of x is equal to 0. And therefore, we have a turning point. For a more convincing proof, you can use second derivative, but considering the complexity of the question and the time constraint on the paper, I do not think that it is necessary. Part 3. Prove that f is an increasing function when c is equal to 0. Okay, so if c is equal to 0, f prime of x becomes 1 plus 1 over x to the x times this. Once again, this part is strictly positive, So, and we also know that if c is equal to 0, then g of x has negative gradient when x is. Let's also sketch this curve. We can also see that it is strictly positive. Therefore, f prime of x is greater than 0 and f is increasing. Part D. We want to show that this limit is equal to e. This is a relatively standard use of L'Hopital's rule. Because f of x is an exponential function, we have to consider ln of this limit instead of the limit itself, so that we can use the L'Hopital's rule. So consider ln of L. Limit as x approaches infinity of ln of L of ln of f of x is equal to this limit. And now we are ready to set up as a fraction. Differentiate the top and bottom. Simplify your answers just a little bit. And we're down to this very basic limit. The numerator is a quadratic, the denominator is a quadratic. The leading coefficients of the quadratics are both 1, so this limit has to be equal to 1. Or you can also do L'Hopital 2 more times. Since the limit of ln of f is equal to 1, the limit of f is equal to e to the 1, or e, as requested. Why is this important? It is important because now we are going to consider this massive equation over here. Because of the word hence, you cannot just graph the function and say that, oh hey, they don't have real solutions. That's not going to work. So let's look at this equation. The numerator here is equal to x plus 1 to the 4. X plus 1 divided by x, that's actually 1 plus 1 over x. So the left hand side, we have this curve. On the right hand side, we have this curve. The limit as x tends to infinity of this guy we shown to be e. And you can also quickly remind yourself that it is monotonically increasing. For the second curve, we note the limit as x tends to infinity of x divided by x of plus 1 is equal to 1. So therefore the limit for the expression on the right hand side is e. However, it is monotonically decreasing. And we can just quickly sketch this curve as well. Oh, okay. So this is problematic. So this is part D2 of question 1 on the N25 paper 3 mock exam. I've noticed a slight typo to the question, so this is the corrected version. We want to show that this equation has no real roots. First, we will need to rearrange the function, the equation. This denominator is actually x plus 1 to the 4. So you would end up with this equation over here. On the left side, I've graphed the function on the right hand side. And as we can see, this curve is monotonically decreasing for x greater than 0, and the limit as x tends to infinity is equal to e. On the left hand side, we showed that the function is increasing for x greater than 0 as c is equal to 0, and the limit as x tends to infinity is also equal to e. So we have one function that is decreasing until it reaches the horizontal asymptote. Another function is increasing. So, just for your reference, let's also graph this guy. This is going to be a right hand side, this is going to be a left hand side. Therefore, they do not intersect. And therefore, the equation has no real roots. And this is the end of question 1.